However, the database administrator will need to have regular access to much of the dictionary system and should have a detailed knowledge of the way in which the dictionary is organized. The Performance Management Subsystem provides facilities to optimize or at least improve DBMS performance. This is necessary because the large and complex software in the DBMS requires attention to ensure it performs efficiently, that is, it allows retrieval and changes to data to be made without requiring users to wait for significant periods of time for the DBMS to carry out the requested action. Two important functions of the Performance Management Subsystem are query optimization, structuring SQL queries or other forms of user queries to minimize response times, DBMS reorganization, maintaining statistics on database usage, and taking or recommending actions such as database reorganization, creating indexes, and so on to improve DBMS performance. The Data Integrity Management Subsystem provides facilities for managing the integrity of data in the database and the integrity of metadata in the dictionary. This subsystem is concerned with ensuring that data is, as far as software can ensure, correct and consistent. There are three important functions: intra-record integrity, enforcing constraints on data item values and types within each record in the database; referential integrity, enforcing the validity of references between records in the database; concurrency control, assuring the validity of database updates when multiple users access the database. The Backup and Recovery Subsystem provides facilities for logging transactions and database changes, periodically making backup copies of the database, and recovering the database in the event of some type of failure. We discuss backup and recovery in greater detail in a later unit. A good DBMS will provide comprehensive and flexible mechanisms for backing up and restoring copies of data, and it will be up to the database administrator, in consultation with users of the system, to decide precisely how these features should be used. The Application Development Subsystem is for programmers to develop complete database applications. It includes case tools, software to enable the modeling of applications, as well as facilities, such as screen generators, for automatically creating the screens of an application, given details about the data to be input and output, and report generators. In most commercial situations, there will in fact be a number of different database systems operating within a number of different computer environments. By computer environment we mean a set of programs and data made available usually on a particular computer. One such set of database systems, used in a number of medium to large companies, involves the establishment of three different computer environments. The first of these is the development environment, where new applications are developed, and new applications, whether written within the company or bought in from outside, are tested. The development environment usually contains relatively little data, just enough in fact to adequately test the logic of the applications being developed and tested. Security within the development environment is usually not an important issue, unless the actual logic of the applications being developed is, in its own right, of a sensitive nature. The second of the three environments is often called pre-production. Applications that have been tested in the development environment will be moved into pre-production for volume testing, that is, testing with quantities of data that are typical of the application when it is in live operation. The final environment is known as the production or live environment. Applications should only be moved into this environment when they have been fully tested in pre-production. Security is nearly always a very important issue in the production environment, as the data being used reflects important information in current use by the organization. Each of these separate environments will have at least one database system, and because of the widely varying activities and security measures required in each environment, the volumes of data and degree of administration required will itself vary considerably between environments, with the production database as requiring by far the most support. Given the need for the database administrator to migrate both programs and data between these environments, an important tool in performing this process will be a set of utilities or programs for migrating applications and their associated data both forwards and backwards between the environments in use. The Security Management Subsystem provides facilities to protect and control access to the database and data dictionary. The benefits of the database approach are as follows. Ease of application development. The programmer is no longer burdened with designing, building, and maintaining master files. Minimal data redundancy. All data files are integrated into a composite data structure. In practice, not all redundancy is eliminated, but at least the redundancy is controlled. Thus inconsistency is reduced. Enforcement of standards. The database administrator can define standards for names, etc. Data can be shared. New applications can use existing data definitions. Physical data independence. Data descriptions are independent of the application programs. This makes program development and maintenance an easier task. Data is stored independently of the program that uses it. Logical data independence. Data can be viewed in different ways by different users. Better modeling of real-world data. Databases are based on semantically rich data models that allow the accurate representation of real-world information. Uniform security and integrity controls. Security control ensures that applications can only access the data they are required to access. Integrity control ensures that the database represents what it purports to represent. Economy of scale. Concentration of processing. Control personal and technical expertise. New specialized personnel. Need to hire or train new personnel. Example, database administrators and application programmers. Need for explicit backup. Organizational conflict. Large size. Often needs large amounts of processing power. Expensive. High impact of failure. Concentration of processing and resources makes an organization vulnerable if the system fails for any length of time. Organizations need data to provide details of the current state of affairs. For example, the amount of product items in stock, customer orders, staff details, office and warehouse space, etc. Raw data can then be processed to enable decisions to be taken and actions to be made. Data is therefore an important resource that needs to be safeguarded. Organizations will therefore have rules, standards, policies, and procedures for data handling to ensure that accuracy is maintained and that proper and appropriate use is made of the data. It is for this reason that organizations may employ data administrators and database administrators. It is important that the data administrator is aware of any issues that may affect the handling and use of data within the organization. Data administration includes the responsibility for determining and publicizing policy and standards for data naming and data definition conventions, access permissions and restrictions for data and processing of data, and security issues. The data administrator needs to be a skilled manager, able to implement policy and make strategic decisions concerning the organization's data resource. It is not sufficient for the data administrator to propose a set of rules and regulations for the use of data within an organization. The role also requires the investigation of ways in which the organization can extract the maximum benefit from the available data. One of the problems facing the data administrator is that data may exist in a range of different formats, such as plain text, formatted documents, tables, charts, photographs, spreadsheets, graphics, diagrams, multimedia, including video, animated graphics, and audio, plans, etc. In cases where the data is available on computer-readable media, consideration needs to be given to whether the data is in the correct format. The different format in which data may appear is further complicated by the range of terms used to describe it within the organization. One problem is the use of synonyms, where a single item of data may be known by a number of different names. An example of the use of synonyms would be the terms telephone number, telephone extension, direct line, contact number, or just number to mean the organization's internal telephone number for a particular member of staff. In an example such as this, it is easy to see that the terms refer to the same item of data, but it might not be so clear in other contexts. A further complication is the existence of homonyms. A homonym is a term which may be used for several different items in different contexts. This can often happen when acronyms are used. One example is the use of the terms communication and networking. These terms are sometimes used to refer to interpersonal skills, but may also be employed in the context of data communication and computer networks. When the items of data that are important to an organization have been identified, it is important to ensure that there is a standard representation format. It might be acceptable to tell a colleague within the organization that your telephone extension is 5264, but this would be insufficient information for someone outside the organization. It may be necessary to include full details such as international access code, national code, area code, and local code, as well as the telephone extension, to ensure that the telephone contact details are usable worldwide. The format of dates is a typical example of an item of data with a wide variety of formats. The ranges of date formats include day month year, month day year, year month day, etc. The month may appear as a value in the range 1 to 12 as the name of the month in full, or a 3-letter abbreviation. These formats can be varied by changing the separating character between fields from a hyphen to a slash, full stop, or space. The use of standardized names and formats will assist an organization in making good use of its data. The role of the data administrator involves the creation of these standards and their publication, including the reasons for them and guidelines for their use across the organization. Data administration provides a service to the organization, and it is important that it is perceived as such, rather than the introduction of unnecessary rules and regulations. The role of the database administrator within an organization focuses on a particular database or set of databases and the associated computer applications rather than the use of data throughout the organization. A database administrator requires a blend of management skills together with technical expertise. In smaller organizations, the data administrator and database administrator roles may be merged into a single post, whereas larger companies may have groups of staff involved with each activity. The activities of the database administrator take place in the context of the guidelines set down by the data administrator. This requires striking a balance between the security and protection of the database, which may be in conflict with the requirements of users to have access to the data. The database administrator has responsibility for the development, implementation, operation, maintenance, and security of the database and the applications that use it. Another important function is the introduction of controls to ensure the quality and integrity of the data that is entered into the database. The database administrator is a manager of the data in the database, rather than a user. This role requires the development of the database structure and data dictionary, a catalog of the data in the database, the provision of security measures to permit authorized access and prevent unauthorized access to data, and to guard against failures in hardware or software in order to offer reliability. A number of different approaches or models have been developed for the logical organization of data within a database system. This logical organization must be distinguished from the physical organization of data, which describes how the data is stored on some suitable storage medium, such as a disk. the physical organization of data will be dealt with in their unit on physical storage. By far, the most commonly used approach to the logical organization of data is the relational model. In this section, we shall introduce the basic concepts of the relational model and give examples of its use. Later in the module, we shall make practical use of this knowledge in both using and developing examples of relational database applications. The first step in the development of a database application usually involves determining what are the major elements of data to be stored. These are referred to as entities. For example, a library database will typically contain entities such as books, borrowers, librarians, loans, book purchases, etc. Each of the entities identified will contain a number of properties or attributes. For example, the entity book will contain attributes such as title, author, and ISBN. The entity borrower will possess attributes such as name, address, membership number. When we have decided which entities are to be stored in a database, we also need to consider the way in which those entities are related to one another. Examples of such relationships might be, for the library system, that a borrower can borrow a number of books, and that a librarian can make a number of book purchases. The correct identification of the entity and attributes to be stored and the relationships between them is an extremely important topic in database design and will be covered in detail in their unit on entity relationship modeling. In introducing the relational approach to database systems, we must consider how entities and their attributes and the relationships between them will be represented within a database system. A relation is structured like a table. The rows of the structure, which are also sometimes referred to as tuples, correspond to individual instances of records stored in the relation. Each column of the relation corresponds to a particular attribute of those record instances. For example, in the relation containing details of stationery on the next slide, each row of the relation corresponds to a different item of stationery, and each column or attribute corresponds to a particular aspect of stationery, such as the color or price. Each tuple contains values for a fixed number of attributes. There is only one tuple for each different item represented in the database. The set of permissible values for each attribute is called the domain for that attribute. It can be seen that the domain for the attribute color in the stationery relation in the next slide includes the values red, blue, green, white, yellow, and black. Other colors may be permitted, but are not shown in the relation. The sequence in which tuples appear within a relation is not important, and the order of attributes within a relation is of no significance. However, once the attributes of a particular relation have been identified, it is convenient to refer them in the same order. Very often, it is required to be able to identify uniquely each of the different instances of entities in a database. In order to do this, we use something called a primary key. We will discuss the nature of primary keys in detail in the next learning unit, but for now we shall use examples where the primary key is the first of the attributes in each tuple of relation. Here, the attributes are item code, item name, color, and price. The values for each attribute for each item are shown as a single value in each column for a particular row. Thus for item code 20,217. The values are A4 paper, 250 sheets for the item name, blue for the attribute color, and 2.75 is stored as the price. The schema defines the shape or structure of a relation. It defines the number of attributes, their names, and domains. Column headings in a table represent the schema. The extension is the set of tuples that comprise the relation at any time. The extension, contents, of a relation may vary, but the schema, structure, generally does not. The schema is represented as. Refer to the previous slide, the stationery table. The extension will vary as rows are inserted or deleted from the table, or values of attributes, example, price, change. The number of attributes will not change, as this is determined by the schema. The number of rows in a relation is sometimes referred to as its cardinality. The number of attributes is sometimes referred to as the degree, or grade of a relation. Each relation needs to be declared, its attributes defined, a domain specified for each attribute, and a primary key identified.